talk about bright line spectra. So the first thing I want you to do is go get your spectroscopes. Get a CDM if there's not a CDM already that allows you to see the spectrum. Yes.
I have assigned 1, 2, and 3.
All right. How you feeling?
Now it's sore.
How's your brain?
Okay, pretty good. Yeah, I understood the lesson pretty well.
There's two things I want you to do with the spectroscopes immediately. I want you to dial in the fluorescent lighting. Then I want you to come back here again. It's a nice sunny day. I want you to dial in the natural light. Get the fluorescent lighting, then get the natural light. And I want to ask you an old term. I want to see what you say.
That was so funny.
Okay, what did you notice the difference is? Which one is quantized? Which one is continuous? Celeste? Okay, so notice that the sunlight all blur together, right? It's hard to tell where red stops and orange begins, and when orange stops and yellow begins. But the fluorescent lighting is a little different. Now the fluorescent light still is continuous in that there are no breaks in it. Do you recognize that? But fluorescent light, of course, isn't the sun. It's a different process. So you would be able to use the spectroscope to see, oh, there's a white light. Oh, but that was made by a fluorescent light. And you'd be able to go, oh, there's white light. That's being made by the sun. So you could use the spectroscope to identify where the white light was coming from. Recognize that? Okay, so today we're going to look at a weird phenomenon known as bright line spectra. Earlier this year, you said you didn't know what this meant. Right here I have a voltage supply. The volts in this thing are 5,000 volts. Now, I don't know if you know what voltage is or not, but you know what the voltage in a typical outlet is. How much? You're close, 120, not quite, but it's down a little bit. 110. 110 out of an outlet. And of course your stove runs off of a slightly greater one. What's that one? Stove runs off an outlet that is what voltage? 220. Okay, so if you touch the electrical outlet on a stove, would you get electrocuted? Is that a lot? 220. 220 volts? Yes, you would get electrocuted out at 220. 110, no, not quite. So I want to put things in perspective. 110, 220. This is 5,000. Okay, you got what that is now. So under no circumstance come up here and touch this. So, okay, so what I have next is a ball that has all the air sucked out of it, and we have hydrogen pumped into it. There's an electrode here, there's an electrode here. There's no electrode, there's no metal that goes in between the two electrodes. So there's nothing in between but a gas. You put that into this high voltage power supply and turn it on. We will get a certain color emitted from the gas. So when you pass electricity through a gas, we get a distinct color. This color is a blend of several colors. Thanks, CJ. Several colors are making this up. All right, now, what you can do to see the colors that make up this light is you could use what device? You could use the spectroscope. If you use your homemade spectroscope, it's going to be a little tricky because these are, of course, homemade. But I would like you to try it. Now, when you do this, you get this slot, try to line that up with that light beam. You have to look sideways and try to see if you can see any colors other than that kind of lavender color. And if that doesn't work for you, I have two backup plans. I have commercially purchased spectroscopes. You can try those. But I'd like to see if you can find it in your homemade spectroscope. Anyone find it in their homemade spectroscope? Well, then maybe you don't know what you're looking for yet. So use the commercially purchased ones. To use a commercially purchased spectroscope, hold it like this, so that notice that one side is angled, the other one is straight. Put the straight side, and at the end of that straight side, there's a little slot. Try to line that light up with that slot, and then holding the spectroscope still and steady, move your head so you're looking down the angle. Line the light up in the slot, hold the spectroscope steady, and then move your head off to the side. Don't forget you, Ashley, sorry. You see it? What are you seeing?
Red, blue, and violet.
You all seeing red, blue, and violet?
In this one, I can only see red.
You can see it in that one now. So now it's showing that you're looking for, you might want to use your homemade one and see if you can find it in the homemade one. Is that spectrum you're seeing continuous or quantized? That is a quantized spectrum, and there's vast areas of the spectrum that you can't see anything, right? Okay, so on your note template, this is a quantized spectrum. Not continuous. Questions so far? Now, every gaseous element tell them we're eating sea lunch today. Alright, so you could identify, so let me put a different one in here. Put a different one and I'll show you. So that was hydrogen. This is a different gas. I'm not going to tell you what this one is. Ooh, neat. The other one back in there, but they give off a distinct bright line spectrum. So there's the first one again. Up, just broken. Back up there. Okay, now, if you look at those different bulbs, you get a unique bright line spectrum. So that is hydrogen that you're looking at right now. So this is the top one on the chart. So hydrogen produces these colors. There's helium, there's mercury, and strontium. Okay, so look at the spectrum again, using your spectroscope, and then notice that it looks like you should see a red, a blue, and they have two light purple ones here. Notice there's vast areas where there's no color being represented. Okay, I'm going to put the other one in there. I want you to tell me what gas that is. Now, in case that's awkward to you, I have a third way you can look at this spectrum. This is just the raw diffraction grating, the same grating that's on the end of the spectroscope. See a little piece of plastic that's on the end? This is that material. If you take this, oh, it's so easy even though, how's that commercial go? So easy even a caveman could do it. Pretty easy now. Do you figure what element that is? Helium. See a red line, a yellow line? Just one or two of them. What's that? You see a green line?
Yeah. Or green line.
Well, that's helium. Okay. All right, now that is a phenomenon known as bright line spectrum. Each element gives a unique one. I will collect your spectroscopes and pass those up to the front of the room. And the diffraction grating also. I will collect those. Thank you. A guy by the name of Niels Bohr explained the phenomenon of bright line spectrum by this model. He said electrons exist in levels. when the atom is hit with electricity, you're adding energy to the atom. The electron goes up, bouncing up in a quantized manner. So like going up a couple steps on a staircase, bounces up. Boom, boom. That absorbs some frequencies out of this electricity. When the electron bounces back down, it temporarily sticks in that level. When it does, it gives off energy of a certain frequency. Niels Bohr proposed that the energy difference between this level and this level was directly proportional to the frequency. Does that look familiar? When it bounces down to the next level, because remember when dun dun comes back down, dun dun, it gives off a different frequency. This frequency would be different than the first frequency. So on a bright line spectrum that you just observed, you might see one band of color, and you might see a second. But you don't see anything in between the two colors, because there's no possible way for the electron to be in those locations. When I was a kid, I didn't have video games, I didn't have YouTube, so I had to entertain myself different ways. One of the ways I entertained myself was I had a ball, and I'd throw it up the steps. I'd throw it up the steps and I'd play catch. So the ball would hit the steps, boom, and bounce down, and it might come down this way. It would come down in an unpredictable manner. Go up there and bounce down in one big jump. Boom, boom, and I'd catch it. Oh, that was easy. But next time I'd throw it up there, it would go boom, boom. And it might hit a couple steps. It might hit this step, skip a step, hit that step. But the staircase is continuous or quantized, Anna. Does it come in pieces? Can you have step 1.5? You're either in step 1 or 2 or 3, but you're not in step 1.5, and there's no step 1 3/4 either, is there? So, it would come down in a series of steps. But you realize that the ball, even though it would come down many ways, could not come down an infinite number of ways. It would hit one step or the next step, or the next step. Or hit the first step and that, but it can't hit in between the step. So when I was playing this game, the ball never, not one time, hit up here on step 4.5 and bounced down. Or 4 3/4. It either hit on this step, or it hit on the next step, or it hit on this step. But it could not hit in between the steps. What would this look like if I could have made the ball hit anywhere? It would not be a staircase, but a wall or a slide or a ramp. So if this were a ramp, then that ball could hit anywhere. And I would get infinite combinations of the ball falling back down to me. Which one is continuous? The ramp or the staircase? The ramp. Okay, now, in Niels Bohr's model, this is a similar situation to the staircase. The electron either goes up a level and back down, but it can't get bounced up to this spot right here and fall back down. How do we know this? What would the bright line spectrum look like if the electrons could be anywhere in the atom? It would be all the colors, right. So we would see not a quantized spectrum, but a continuous spectrum. We don't see a continuous spectrum, so that indicates that the electrons are in levels. So the next thing we want to tackle is the idea of the energy level diagram. We made graphs in the computer lab with ionization energy. And we saw earlier that ionization energy was the energy required to remove electrons from atoms. You can do this successively with, say, a calcium atom. You can blast off all 20. What's one of the trends we saw when we graphed that? James?
Took more energy, the less electrons there were.
Took more and more energy successively. As there were less electrons, it took more. Okay, so it takes more and more energy to get each successive electron off the atom. There's a more important trend, though, that we observe. Can you take out those graphs and take a look at those? Okay, you see anything unusual about this? Yes, it takes more energy to get each successive electron off. Yeah. There's a few steps in this thing. All right, so before we go further, which electrons are easiest to remove and which ones are toughest to remove? It's a very easy question. Easier to remove, tougher to remove. Steph? Are they, can you point to, are these up here or are they down here? They're these ones. These are easier to remove. And so we can look here, we go, there's one that's kind of easy and the next one's pretty easy to remove. And then it looks like there's, how many in a row? 8. We got 8 here. How many in this group? Brianna, how many? 8. And then we have, how many up here? 2. So these are the toughest to remove. The ones that are up there are toughest to remove, and these are easier to remove. Now, when you look at data like the bright line spectrum, and you look at data like ionization energy, you got to realize these came from 2 different places, 2 different, like, this is very different than the ionization energy data, isn't it? But they both end up kind of saying the same thing, don't they? Let's consider this. So we have an atom. The atom has a nucleus. This is a calcium atom. These 2 electrons that are the hardest to remove, what level would you put those in? The hardest to remove. Recall that the nucleus is positively charged. CJ.
The one closest to the nucleus?
Those 2 electrons are in this level closest to the nucleus. Make sense to you? Because the closer it is to the charged particle, the harder it is to remove. Consider 2 magnets. Ashley, hold that magnet, please. It's far, I'm pretty far away, right? Do you feel it pulling on it? No, not at all. How about now? Can you feel it when it gets closer? So the closer it is to that oppositely charged particle, the greater the force of attraction. So it's harder to remove those two. And then, in the second level, what would you propose goes in the second one? Jack? The next 8 electrons. A little easier to remove, but still kind of hard to remove. So these correspond to the 8. Then it looks like there's a jump. Much easier to remove the next group. How many go in that group? Anna? 8. And finally, there seems like there's 2 electrons. They're relatively easy to remove. Ashley Carabini, where would those go? In the outer level. Okay, so we can come up with the idea, we can support the idea that Niels Bohr proposed, that electrons are in energy levels, by looking at completely different data that is also explained by the idea of the energy level. Now, if you do this with every element on the periodic table, you'll notice a similar trend. So we just looked at the data of calcium. Rather than plotting all the data and showing this to you, we're going to have to, I'm just going to jump to the conclusion that it all ends up with similar patterns. We always notice that the second energy level can hold no more than 2. Regardless of the element that we use. So 2 is the maximum that can be in that first level. We can have less than that, but no more than that. And level 2 can have a maximum of 8. Again, I'll repeat. When we do the same data with other elements, we get the same result. We get the same types of graphs. The first level, we notice there's never any graph where there's 2 that are really tough to remove. Level 3, 8. I'm going to put a little asterisk here because I'm not filling you in on the whole detail. This is on a need-to-know basis. There's more detail to this if you take advanced chemistry. So right now, just go, okay, it's 8 as far as we're going to go. And as long as you don't go beyond calcium, that'll hold true. Okay, now we've got to name a few things. The outside level of electrons are known as the valence electrons. We have 2 atoms that are bonded to each other. And if, when we have a chemical process, the bonds are changed, the organization of the atoms is different, then which level of electrons is probably the most important set of electrons to talk about that's going to actually connect and physically touch the other atom? The outer level. So the valence electrons are going to be the most important electrons that we're going to discuss. The inner ones are important, yes, but the outside ones are the ones that are going to be involved in a lot of different things. And you can only appreciate the valence electrons if you understand the levels. So this is going to be super simple. We're going to draw energy level diagrams for oxygen, sulfur, and lithium. So here's how you do it. I would like you to use the symbol of the element for the nucleus. So we use an O to represent the nucleus of oxygen. And then we will draw energy levels around it. I'll draw 1 and I'll draw 2, and we'll see what we have to do with this. Maybe we have to erase one, maybe we need another one. We'll look. So on a periodic table, how many electrons does oxygen have, Brianna? 8. So we have 8 electrons to place. The first level can hold a max of 2, so we're going to fill it up first. Always start in the lowest one and work your way out. So how many will go in this one, Jeff? 2. So I'd like you to write 2e minus right on that line, not between the lines, because that would indicate that electrons are just in between levels. So the line represents a level. Put the electrons in that level. We have a total of 8, so how many are going in the next level? Alicia? 6. Done. An energy level diagram of oxygen. How many valence electrons are there? Sam? No. Valence electrons are those electrons that would bump into another atom. If that atom bumped into one. 6. There are 6. Good. 6 valence electrons. Sulfur. Julie, how many total electrons for sulfur? 16. Okay. Energy level number 1. How many electrons will go in that one, Ashley Moore?
2.
Electrons. Good. And Celeste, how many will go in that second one? It gets filled up before you put it in the third level. Will we fill it? Celeste? We have 16 total. We put 2 in the first level. Can we get 14 in the second one? No, it only holds how many? 8. So 2 and 8. We have to get up to 16. How many will go in the next level, Peter? 6. You see what I mean by the first level can hold a max of 2, the second level can hold a max of 8, and then all the rest go in the next level. Okay, pretty easy, right? Now there are things we do in this class that are kind of difficult. And some people get it, some people don't get it. But I want to explain this to you. This is the thing I need everybody to be able to understand this. Because we're going to use this when we talk about bonding. We're going to use this idea when we talk about flame tests and many, many other things. So it's very important to understand. You have to master this concept. When we draw molecules, we're going to be using the valence electrons to make predictions of how molecules are built. We have one more example to go through, don't we? Lithium. Lithium is pretty easy. So, how many electrons for lithium? Joy? 3. How many will go in the first level, Julie? 2. 2. And Anna, how many will go in the second level? 1. How many valence electrons for lithium? Hannah? 1. Good answer. Okay. Any questions about it? Drawing energy level diagrams. Your assignment is twofold. I want you to draw an energy level diagrams of the first 20 elements on separate paper. For easy reference. I'll give you that paper. So how many energy level diagrams are going to go in that paper, Jack? No. First 20 elements. Try again. 20. So spread them out. You don't have to, there's no sense of crowding them up into the corner. Make them pretty big. Did I give you the whole stuff that holds in it? I did. Stuff that holds in it. Concrete. Good. The second thing I want you to do is to draw an ionization energy versus electron removed Remember, like the graph we made in the lab. And so to kind of reverse it, you have to draw, what we have to do first in the second question, you'll have to draw a we'll have to draw for this one. It says draw an atom with 9 electrons and explain why it looks this way. What will you have to draw? You have to see what its diagram looks like and then work backwards. So we use the graph of this to figure out the energy level diagram. If we use an energy level diagram to figure out what the graph looks like. Just reverse it. See what you're doing. Good so far. Just make sure you do it right. Good. Can't see this one. You just keep doing that and you've got it. 1, 2, good. Alright, you got it so far. Very good. Very good. Everybody looks like you got it.